Okay, let's have a look at homework 6, problem 3, which is about mathematical modeling, and it's very similar to the problem that you have for your final project. So what is the question? It's a lengthy question, actually. So it says, this is what we will want to achieve. We have a data set inside of this MATLAB file, drand.mat. Okay, so if you download this file, then you can, so this is what you do. You download it. It already exists in my folder, in my desktop, so I'm going to skip this part and then look for the data set here. So I have it here, drand. Now, okay, so I can either, okay. Now I want to load this data set and have a look at the content of it, drand.mat. So you can also do the same thing. Download this data set from the web and put it in the MATLAB working directory. And now how do you load the data inside of this file? Load, right. And if you don't want to switch to the switch your working directory to the folder that contains this file, you don't really need to change the working directory. So you can just simply say load, and then here you give MATLAB the exact path to the file. That doesn't need to be necessarily the working directory. But if you say drand.mat, simple as that, without any directions about where to look for this file, then MATLAB is going to look at the working directory by default. And if it's not there, then it will not search anywhere else. Okay. So if I type load drand.mat, it's going to load it for me because I'm already in the working directory. The working directory is already the folder that contains this file. Okay. So CLC clear all, close all. Now I want to load this file. I load it. It gives me a structure drand. Okay. Now let's have a look at it and see what it is. It's 100 by 1 double. Okay. That means I can plot it. Let's plot it and see what we have inside of it. Okay. That's just a set of random numbers. That's what you would expect. It all looks like a white noise. This is called a white noise, actually. That's just a random Gaussian number around 0. And a more useful plot of it is histogram. So if I say histogram drand, then you get a histogram plot of it. Okay. You could also, so here's the problem that we're going to solve. So if you look at this shape that we have here, it looks like, what shape does this look like for you? It's a bell shape, right? It's almost like a bell shape. So it's actually called Gaussian distribution. It has an equation. The equation is e to the power of negative x squared with a couple of factors, constants. That doesn't matter much. But the form of it is e to the power of negative x squared, and x is this value. Right? So if you have e to the power of negative x squared, where is the maximum of this function? It's a 0, right? Because if you set it to 0, then e to the power of 0 is 1, right? So at 0, you get y equals 1. But then at other values, let's take the limits and see what happens. If we set x to infinity, you get e to the power of negative infinity, right? So that means it's, so if I set x to positive infinity, you get y equals 0. How about the other one, negative infinity? That gives you the exact same thing, right? Because negative infinity to the power of 2 is positive infinity. E to the power of negative infinity then is again 0, right? Does it make sense? That's for you? Okay. So that's exactly the kind of behavior that we see there. We have a distribution that has a peak at around 0, and it has tails that go to 0 value at infinity. Okay. So this is our hypothesis. Based on just looking at this graph, we say that the distribution is probably Gaussian. But that's not what we want. We want to quantify it, and we want to really test it and see if this is really the case or not. For this simple example, it's easy to say it. You can just test it with hist fit. So you could say hist fit drand. And then you get a histogram of data. On top of it, the Gaussian fit to this data set. Okay. You could try other things. You could, for example, by default, when you don't specify your hypothesis, your distribution, MATLAB assumes it's Gaussian. Okay. But I could say something else. I could say, for example, uniform. No, I don't think if uniform is a good choice. So hist fit drand log n. That's not going to work, but let's try it and see what happens. Yeah, you see, so log n is a log normal distribution, and its range is always bigger than 0, so that doesn't work for this Gaussian distribution. Anyway, you can always test your the shape of your distribution with hist fit. So if I say here normal, I think this should work. I don't remember exactly, so we have to look at the manual and see what hist fit. Hist fit data, n bins, and distribution. Okay, so I was missing n bins in my example. But basically, this is the function that can fit different distributions for you to your data set. So you can try other things. You can try beta distribution. Many of these distributions you may not be familiar, but that's fine. In future, when you go to your real work, research, or I don't know, industry work, then you will have to use these sorts of distributions. Anyway, that's not our problem. So we know now that this data set is probably well fit by a Gaussian. But here's a question. What's the width of this Gaussian distribution, and what is the mean? How do you find it? MATLAB has actually found it for us, but that's not what we're going to do, because not always we have access to this fancy function, hist fit, that could give us this fitting, and then you could probably also extract the parameters of this distribution, but that's not what we want for now. So how do we get the value, the width of this Gaussian and the height of it, using our own methods? Any suggestions, any ideas? F-min search, okay, but before that we'll have to define an objective function. So in the entire scientific field, wherever you're going to work, the first thing that you have to do for your problem is to define an objective function that you will subsequently maximize or minimize. So this is called optimization, and that's really the bottom of the entire scientific field. So everywhere you go, all your life, even nature itself, what it does is that it's just optimizing something at every moment. So the fact that, for example, you want to go get out of this class, and you're, for example, sitting there, and you look at the two doors, your brain subconsciously optimizes the time it takes to get out of this room, and then chooses this one, because it sees like, with this speed and this direction, I'm going to get out of this room faster than the other one, right? So optimization is almost everywhere. In the brain of animals, in human, in nature, even you, like, for example, you look at the river, the flow of water in the river. Why does the river go downward all the time? It's because there is a potential, there is a gravitational potential. It's like a shape of a ball. And then there is this property inherent in nature that says, just always look for the position that gives you the lowest gravitational potential. And that's what the water molecules in the river do. They just look around and see where it gives them the lower potential for the lower gravitational potential and then move in that direction. So that's why the river doesn't flow upward, because it's going toward a higher potential, right? So again, the point is that you always need to maximize or minimize something, right? So now with this problem, let's see how we can solve it and find the mean and the standard deviation. So if you look at the Gaussian distribution, so this is the shape of normal distribution for different parameter values. And if you look at this, the PDF, the probability density function, the equation for Gaussian distribution, it has two equations, two parameters. Does anybody know what those are called? Yes.
The mean and variance?
Yes, the mean and variance. So this Gaussian distribution has a mean, the parameter mu here, and then I don't know if that's big enough for you to see it. So this is the mean, the parameter mu, and then this is the variance or standard deviation. So standard deviation is the square root of variance. So sigma squared is called the variance, and sigma itself is called the standard deviation. What does it give you? Sigma gives you the bit, the approximate bit of this distribution. So if you have a enormous sigma, what does it mean? It means the points are really spread in this histogram. So the width of this histogram is too wide, right? And how about the mean, mu? It gives you just the average. No, it gives you the average. So it says, on average, for example, what is the mean age in this class? It's probably around 18 or 19, I would say, yes? So that's the exact same thing. So if you plot the age of people in this class, you're probably going to get a histogram like this, and the average age is around probably 19 or 18. In this case, the average looks like to be around 0. Okay, so that's our hypothesis. So our hypothesis is that this distribution is coming from a Gaussian distribution with mean 0 and probably a standard deviation of 1. So if you look at the bit, you see the half bit is almost 1, right? So that's our hypothesis. But now, how do we test this hypothesis? How can we see if that's correct or not? So we can create an objective function for our problem. So one other question. How many of you have seen histogram before? Okay, so is there anything new in this plot for you? Do you understand? Like, for example, what does it mean if you have 15 for the value of this column here, this rectangle?
15 points of this one.
So that means, yes, exactly. We have 100 points in this sample that I showed you. So if you look at the variable drand, you see there are 100 numbers here. Okay. Now, if I put all of these 100 numbers, you see each one has a different value, but most of them are around 0. Okay. So if I plot them, if I put them all on this axis, and then see how many of them fall between 0 and 1, then that number is 20. So 20 of these numbers fall in the bin that goes from 0 to half, and then 23 of them fall between half and 1, okay, and so on. Okay. So how many points are in below negative 3? 0. How many are above 3? 0 again, right? So the maximum number of points you would expect it to be where? At around 0, right? Why? Because if you look at the Gaussian distribution, it says e to the power of negative. When is the maximum of this function? Where is the maximum? For what value of x? 0. So if you set x to 0, then you are going to get the most number of points. Y equals 1. And that's exactly what this equation predicts for us. It says you would get the maximum number of points at around 0. And that's exactly what this graph tells us, right? Okay. So now I ask you one question. Again, just keep in mind that what we want to find is the mean and standard deviation, the width of this distribution. Okay, this is our question. right? We don't know these two parameters, and that's what we want to find. But here is how to solve this problem. Let's assume for a moment, let's assume that we know these two parameters. Let's say we know that the mean is, let's say, 1, and the standard deviation is 10. Okay? Now, I ask you, tell me, what is the probability of observing one of the points that we have in this data set to come from this distribution that I told you? So if you look at the equation for Gaussian distribution, what does this tell you? This is the probability density function for Gaussian distribution. It says if you know mean and if you know the standard deviation, then the probability of getting a specific number x, this one here, is given by this equation. So now, let me ask you this. Let's say mean is 0 and standard deviation is 1 in this equation. Okay? What would be the probability of getting a value of 100? Just tell me if it's big or small or what is it. So the mean is 0, sigma is 1. Okay. Now, what is the probability of getting a value x of 100? It's almost 0, right? So approximately it's about e to the power of negative 100 divided by 2, right? Because see what happens if so mu is 0 and the standard deviation is 1. So then according to this equation, I have the probability. By the way, in the field of statistics, pi represents probability. It doesn't represent the number pi. So if you look at your project, you will also see a lot of symbols pi that represents probability. But whenever it appears by itself without parentheses, that means a pi number. So here we have pi, the number, and here what I'm writing is the probability. So I say the probability of getting a value of 100 given mu equals 0 and sigma equals 1 equals to what? Can somebody read it for me? 2 pi e to the power of negative x squared divided by what? 2. Okay. So let's reread this equation. What does it say? It says the probability of getting a value of x equals to 100, given that I know that the mean is 0 and the standard deviation, the half width of this distribution is 1, is given by this equation. And x is here 100, right? So I could write it as x equal to 100 to the power of 2. That's actually way smaller than what I said. So it's e to the power of negative 10,000, right? That's a huge number. I mean, a tremendously small number. That's what I meant. So, I hope that gives you some ideas. Now, if I want to find the probability for all of these events, what should I do? Given the parameters of the equation.
Would you first assume the parameters of the probability density function? Like,
yes. Let's say we know it, and let's say we know that the mean is 0 and the standard deviation is 1. Okay. Then I ask you, what is the probability of getting each individual point that I have in this data set? The first one, the second one, the third one, and so on, up to the 100th point in this data set. So what would you do? You just write a for loop and then apply this equation to it, and then you get a set of probabilities, right? So let's do this now. So open your MATLAB and then try this. Let's say, first of all, we want to load the data set, right? So we have loaded already the data set. This is what we have. Okay. Then the name of the variable is drand. Okay. So what I can do is that I want to create an extra data set. I don't like drand name, so I want to rename it, copy the data set into a new variable called data. Okay. Now, Let's name this temp. Now, each member of this data array contains one random value from Gaussian distribution. So one of the points that construct this histogram. Now, so what do? We say for I equals 1 to, how many points do we have? So I always define the number of points at the beginning of the program. So I say n pnt or n sample equals length of what? Data. Okay, great. So, and then what I do most often is that instead of using I told you I stands for the negative square root of -1. So it's a complex number in MATLAB. So let's just avoid redefining I. We can say I sample that goes from 1 to n sample, close the for loop, and then go in between. Press tab, and then we want to get the probabilities, right? Here's one thing with MATLAB. For a lot of distributions, MATLAB has the PDF, the probability density function, already coded for you. So you don't need to code what I just showed you here. Okay? You don't need to code this equation by yourself. There's a function in MATLAB called norm PDF that gives you this probability. Okay? So we can test it and see if that's the case. For example, first of all, we need to define the two parameters of mean, which is 0 in our case, and stdev, the standard deviation, which is 1 for the moment, right? So we assume that the points are coming from these two parameter values. Now, if I wanted to implement this equation, I could do it by myself on the command line and say, how would I calculate this? I would say exp of negative 10,000. Let's go with a smaller number. Let's just choose an x value of 1. Okay, so I say x equals 1. Then I say exp of negative x squared is what then? It's just 1, right? Divided by 2 is half. So I get negative half divided by the square root of, what is it? 2 times pi. Okay, so this is the number that we get. So the probability of getting a value of 1 for x, given that the mean is 0 and the standard deviation is 1, is this number. Now let's test this with the MATLAB built-in function for norm PDF, for normal distribution. So I could say norm PDF of 1, the x value, the mean, and the mean and STF are not defined. So let's just set them manually. I would say 0, and then the standard deviation is 1. You see, it gives you the exact same number that we calculated. Oh, you don't see it? Okay. Thanks for speaking up. So talk, guys, talk to me and say you don't see something. Okay. So do you see it now? That's what I did. So this is the equation that we wrote there. That gives the probability of getting a value of x equal to 1, given that mean is 0, standard deviation is 1. And this is the norm PDF, the built-in function in MATLAB, that gives us the exact same number. Okay, so now we can trust this function. So this function, norm PDF, gives you the normal probability density function given 3 values. The first value is the x, the random value that you want to get. The second one is the mean. So if you wait here for a second on this function, it's going to tell you what to write. So the first value is the random number value. The second one is the mean of the distribution. and the third one, sigma, is the standard deviation. Okay, so what I can do is that I want to rename it to MATLAB notation. So I have the data set, I have the mean, sigma, the number of samples. Then how do I get the probabilities of individual points? So all I need to do is that I can create a vector name prob equals zeros of n sample, right, by 1. Okay, now prob I sample equals to, what should I write here then? Norm PDF of what? Yes.
In your command window, did you set x equal to something?
Yes, I set x to equal 1. X equal to 1, yes. So, but here, what should we write instead of x? So prob of I sample is, so I would say norm PDF of data I sample, and what else? The mean and sigma, right? Which name do you like most? The more than the other? Like, is it sigma or standard deviation? STDEF. Which one is more? STDEF? Sigma. Okay, so let's go with sigma. Right. And then how about mean? Mu or mean? Mean? Mu, mean. What? Mu. Okay. Okay. So let's go with mu or mu. All right. So now, if I run this code, I'm going to get a vector prob that contains the probability of getting each one of these points in my data set, given that mean is 0 and a sigma is 1 for a Gaussian distribution. Okay? Now let's run it and see what we get. Okay, we got it. So we have a prob now. And now, what would I get if I plot prob? I wouldn't get anything beautiful because the numbers are randomly spread in the data set. So what I can do instead is that I can say scatter, not a scatter, I would say plot prob using dots. Okay, that doesn't look good. I think we made a mistake, and that is, what is the x value? So we have to plot data versus prob. That would make it much more beautiful. You see how beautiful it is now? So what happened in this plot? Can somebody explain me what we are plotting here? So let me make it a little bit, so I would say marker size is, let's set it to 15 or maybe 20, and then marker color, or color simply, is red. Okay, now it looks like this. So what does this mean? This is a plot of probabilities that we got versus x, the data values. So what does this mean really? Can anybody provide any explanation? No suggestions? Yes?
It's like the probability
Of getting that value.
of getting a certain value by value.
Exactly. So we have all these different values in our data set that goes from some negative value to some positive. So like if you look at this data set that we have, what we are doing in this plot is that we are plotting the set of numbers, random numbers that we had, this column, versus, not versus that, the probabilities of getting those numbers versus their values. Okay, and you would expect it to look like a Gaussian distribution, right? So at the beginning we said that our hypothesis was that it comes from a Gaussian distribution, and this is what we get. But now here's one question for you: why do we get so few points here in the tails and so many points at in the head of this function at the top? Exactly, yes. So if you look at the previous graph, the histogram that we plotted a few minutes ago, so let's create a new figure handle, and then in this one I'm going to plot his fit. Okay, not this one, his fit. Okay, now here, see, basically what we have done here is that we have plotted this red curve that MATLAB calculated for us here by ourselves using just the data set that we have. But the reason we have so many points at the top of this curve versus the tails is that we have so many points in our data set that come from that highly probable region at the top, right? So if you recall, I showed you that many of the points fall in this region, right? So a lot of points are here, and then a few of them are in the tails. So basically this red curve, or this one here, just shows how frequent the points appear in our data set. So if they are close to 0, a lot of them occur around 0. That's what we get. And then a few of them are in the tails. And that's a characteristic of a Gaussian distribution. Okay, so now here's one thing. What if I ask you what is the probability of getting all of these events, all of these points together, rather than just every single of them? So how would you calculate the probability of getting all of them together? So these points are independent of each other. So if let me ask you this question. I ask you to flip a coin twice. Then I ask you, what is the chance of getting 2 heads in the 2 flipping? So what is the chance of getting a head in the in 1 coin flipping? It's 1. No, it's 1.5, right? So it's half. So then, what if you wanted to get it another time? That's another half, right? So what is the probability of getting 2 heads in coin flipping? It's 1/4, right? So you see, you basically in your mind, you're multiplying the probabilities with each other, right? So that's exactly what you need to do here. So you say the probability of getting the ith data point in your data set is this. The probability for the next one and the previous one is also given. So now you ask the question, what is the probability of getting all of these points together? Right? Does it make sense for you? But then, what would you expect to get? I think it would be a really small number. So all we need to do is, there's a function for multiplication. What is it? Prod. Excellent, excellent. So I would say prod of prob. So this number, which is extremely small, is 10 to the power of negative 62. This is the probability of getting all of these points together from this Gaussian distribution that we hypothesized to be correct, right? So because this number often is really small, people do one more interesting thing to these probabilities. Instead of calculating the probability, they calculate the log of it. So remember from the one of the quizzes, I asked you to find another way of getting the factorial. When the factorial is too large, what should you do to not go beyond the machine precision and the machine limits? So suppose, for example, we had 1,000 points in our data set. Then this number would have become extremely small, 10 to the power of negative 1,000. You want me to try and show it to you, or is it understandable? You see it? So like with 100 points, we get such a small number. So if you try with 10 times more, you can test it yourself. You will get a 0 here. So that doesn't make sense. You have got these points, and yet MATLAB tells you the probability of getting these points is 0. That just doesn't make sense. It's not 0. It's probably so tiny that MATLAB cannot represent it correctly. So what is the solution to this problem? You take the log. Then, what is the log of 10 to the power of negative 62? Negative 62, right? So instead of getting such a small number, tiny number, you get the exponent of it, and you represent the probability by its exponent. And whenever you talk about probability, you know that you have to take the exponential of the number that you have in order to get the probability. So what I can say here is that I can say take the log of norm PDF, and then the total probability is just what, and then I'm going to rename this also in order to note that this is not probability anymore. This is log probability. So then what is the total probability then? Total log prob. It's sum now, right? So here's the thing. When you take the log of an equation, product turns to a sum. So let's see why this happens. So here's one simple exercise for you guys. I ask you, so y is 10 times 10. Okay. Now, what is the log of this value? The log 10, log in base of 10. It's 2. Why 1? So 10 times 10 is 100. What is the log? No, yeah. So okay, that's good, but not for now. So the log of y is log of 100, which is 2, right? Now, going back to your point, what is the log of 10? What is the log of 10? 1. So now, I could write this equation as this. Log of y is log of 10 plus log of 10. And each one is 1, right? So that also gives you 2. So you see, taking the log of an equation turns the multiplication to a sum. Okay? So now, if I ask you what is the log probability of getting all of these events together, all of these points together, then you sum over the log probabilities instead of multiplying them with each other. So if I ask you what is the log probability of getting 2 heads in two coin flipping experiments, what do? You add log of 1/2 plus log of 1/2 instead of multiplying 1/2 by 1/2, right? So I say sum of log prob is what we want. Okay, so now test this. Interesting. You get so I see what happened. So see, this number is 10 to the power negative 62. But we took the log of it, and now we have 142. Why does this happen? We took the log, so it should give us negative 62. Why is the number different? Yes. Exactly. Excellent. Yes. So the problem is that we used the wrong base. So we could, if we had said log 10, then we would have got the correct number, which is negative 61, right? Still different a little bit, but that's close. And the difference is why do you get such a small difference? It's not a big difference actually, though. So if you take the log of this number, it's exactly this one. So it's not exactly 10 to the power of negative 62. It has some residual left, right? So now we have done the first part of the problem. So if I tell you the mean and the standard deviation for the normal distribution, you should be able to give me the probability of getting all of the points from this normal distribution. The log of it, actually. Okay. I don't like log in base of 10, and nobody likes it. So I also encourage you to not use log in base of 10, except for illustration, like plotting, and nothing other than that, right? So what is the inverse of log? If you want to go back to the original quantity that you had, you do an exp, right? So the inverse of log is exp. What is the inverse of log 10? 10 to the power of the number that you have, right? And 10 to the power of something is very ugly, so you want to avoid it all the time. Okay, so now this code gives you the probability of getting the data set that you have with this given mu and sigma. Okay, now why not convert this function to this script that we have written to a function, so that whenever we call this function, it gives us the probability of getting the data set that we have, given the specific mean and sigma values that we give it. Okay, so what I'm going to do is that I define a new function, get total log prob. Okay, so function equals total log prob equals get total log prob. What are the inputs to this function then? What was that? Excellent, yes. So we have mean and standard deviation. We named it mu. So mu and sigma are the input. And then in between, what do we get? So we calculate the probability, the log probability of getting all of these events. Okay, so log prob, we initialize it, and then we define the for loop again here, and then total log prob is the output of this function. Now, if I say get total log prob, here's a problem. So in this function, I have data variable, but data is not given to this function. It's not defined. So how do we pass data to this function? Should we pass it through input argument or any other suggestions? We could define as a global. Excellent. Yes. So what I can say is that I can say right at the beginning, global data. So data is a global variable, right? And then here, as soon as I read it and define it, so here I say, you should note that when you want to define a global variable, you have to define it before you use it for the first time. So you define the data variable as global, and then you put some values in it. Okay. Now I can say call. Once I have this data set, I'm gonna skip reading it every time, right? So now I say get total log prob with this mu and sigma. Okay, now if I run this, it will calculate the probability and give it to me. Okay. What happened? There's a lot of errors. The value of local variables might have changed to match the globals. Okay, let's... Oh, there's another problem, friends. What is it? N sample is not defined inside of the function. So we could also define n sample as a global variable, right? So let's define n sample also as a global variable. N sample. Okay. So the way to define multiple global variables next to each other is just to add a space between them. So global data, n sample, both of them. And now let's run it. Okay, now we get the number that we want exactly. Okay. So it says we use the global variable before we define it. I don't see anything wrong with our work. CLC, clear all, close all, CLC. Okay, now call temp again. Okay, now it works. Okay, now let's say we want to change the input variable to something. So let's set mu to 1 and sigma to 10 and see what happens. We get negative 323, right? So you see, for each value of mean and sigma, we get a log probability for that data set. Okay. Now, the last thing that has remained in our work is to give this function that we have created. Basically, we have created an objective function that takes the data set, takes the value for mean and sigma, so 3 input quantities, and then it calculates the log of the probability of getting that data set, given those parameter values. Now, the remaining part for this part of the problem is to give this function to fmean search in MATLAB. and then let MATLAB find the set of parameters that give us the highest log probability. Okay, but here's one catch. If you try this with MATLAB, it will give you nonsense result. Why is it so? Because MATLAB f-mean search searches for the minimum value. We want to find the highest value in our probability density. Okay, how do you find the highest value? -1. You multiply your function by negative. Okay, so see, if you have a function like this and you want to find the maximum of it, what would you do? What would you do to this function to get a maximum of it? If you multiply this function by negative, it's going to look like this. The maximum or the minimum value is not going to change. So if you find the minimum of this function, the negative of the function that you are searching for, then you will find the maximum of the correct original function, right? So all I need to do here is to multiply the log likelihood that I have here by negative value. So I say negative sum. And that's it. All I need then is to pass this. So now if I run this code again, temp, it's going to give me a positive result because I have multiplied the likelihood by a negative sign. So now our goal is to pass this function that I have written, get total log prob, to f-mean search in order to find the best fit values for my function. So I say, this is the last thing we're going to discuss. F-mean search, what is the function that we're going to pass? Get total log prob. So you should also give it some initial search values for mean and sigma. So let's give it sigma of 1 and standard deviation of 2. There is one thing. You have to give it as a vector, not single values. So you have to define a parameter vector instead of mean and sigma. So you would say param equals mu sigma. And Cameron and you who are leaving the room, I forgot your name. What was it?
Henry.
Henry, yes, Henry. I want to talk to you after the class, if you have time.
Yeah.
So, thanks. And then, so I define param, and then I change my function so that it takes param, not mean and sigma. So I say take param, and then the first, instead of mean, I pass param 1. Instead of sigma, I pass param 2. Okay. That's it. And we are done. So now if and instead of this, I pass param. Okay. Not param 1, just param. Both of them. And here I pass param again. So instead of mean and sigma separately, I'm passing all of it as a vector. Now let's comment this line and see if the code works fine. Yes, it works fine. It works perfectly fine. Okay. Now, the last step is to just run this code and find the set of parameter values that give us the best fit, the best parameters for this Gaussian function. And here is the answer. So f-mean search found the best mean for our function, for our histogram, to be negative 0.08, which is very close to 0, right? And the standard deviation to be 1. So that means the best fit to our problem, hist fit of data, the mean, if you look at it well, you see that the mean of it, the peak of it, is a little bit off the 0 point, right? So the mean is actually negative 0.08, and the standard deviation pretty much is 1. Okay? So these are the best values of the Gaussian distribution for this data set. Okay? So we have solved problem 3, and that's exactly what you need to do for the project, except that the mean there is not given by a single number. The mean there is given by a physical model called Gompertzian. So we will discuss this next time more. But I hope you learned something here. What was the question? You had a question? Okay. Henry.